A cat is penned up in a steel chamber. In a Geiger counter, there is a tiny bit of radioactive substance, so small that perhaps in the course of the hour one of the atoms decays, but also, with equal probability, perhaps none. If it happens, the counter tube discharges and through a relay releases a hammer which shatters a small flask of hydrocyanic acid. If one has left this entire system to itself for an hour, one would say that the cat still lives if, meanwhile, no atom has decayed. The psi function of the entire system would express this by having in it the living and dead cat, pardon the expression, mixed or smeared out in equal parts. Schrödinger's cat is a legendary thought experiment that lies at the very heart of quantum physics. Conceived in 1935 by Austrian physicist Erwin Schrödinger, it was never intended to describe the behavior of actual cats, but to reveal how absurd and unsettling the implications of quantum mechanics become when extended from subatomic particles to the macroscopic world of everyday objects. At its core, Schrödinger's cat illustrates the strange notion of quantum superposition and the so-called measurement problem, forcing us to question what we mean by reality itself. Imagine a perfectly sealed steel box. Inside is a living cat, a small container of radioactive material with a 50% chance of decay within an hour, a Geiger counter to detect that decay, a vial of deadly poison gas, and a hammer connected to the detector. If the Geiger counter picks up radiation, it triggers the hammer to smash the poison vial, killing the cat. If there's no decay, the cat lives. According to classical logic, after an hour the radioactive atom has either decayed or not, so the cat must be either alive or dead. But quantum mechanics tells us something radically different. In the quantum realm, particles exist not in definite states but in combinations of possibilities. This is called superposition. A single atom can be simultaneously decayed and not decayed, at least until we observe it. Extending this logic to the cat, we're forced to accept that, until we open the box and check, the entire system is in a superposition. The cat is both alive and dead. It is not that we don't know which state the cat is in, the cat genuinely exists in both states at once as long as the system remains unmeasured. Only when an observation occurs does the superposition collapse into a single, definite state. This idea, so contrary to common sense, was precisely what Schrödinger sought to highlight. The thought experiment was a critique of the prevailing Copenhagen interpretation, advocated by Niels Bohr and Werner Heisenberg, which accepted wave function collapse as a fundamental feature of quantum mechanics. Schrödinger found it troubling that such a collapse seemed to depend on observation, which introduces subjectivity into physics. Does it require a conscious observer to cause collapse? Could a cat's awareness be enough? Or does the universe somehow know when it's being measured? This leads us to the so-called measurement problem in quantum mechanics. When and how does the transition to a definite state happen? And what counts as a measurement? The cat scenario is an extreme magnification of this problem, revealing how bizarre the consequences become when quantum law objects. Several interpretations of quantum mechanics attempt to resolve this issue, each providing a different perspective on Schrödinger's cat. The Copenhagen interpretation simply states that the cat is in superposition until an observer looks, and only then does the state become definite. The many worlds interpretation offers a radical alternative. It posits that both outcomes occur, but in separate branching universes, one where the cat lives, and another where it dies. Reality continuously splits into parallel histories, each representing a different outcome of every quantum event. According to this view, when you open the box, you are also splitting into versions of yourself, each experiencing a different result. Another approach is decoherence theory, which argues that superpositions exist, but interactions with the environment destroy them almost immediately for large systems. In this view, the cat is effectively either alive or dead long before anyone looks. The superposition becomes entangled with countless environmental variables, making interference, a sign of quantum behavior, impossible to detect. Then there are objective collapse models, which propose that superposition is inherently unstable for large masses and collapses spontaneously without observation. Finally, quantum Bayesianism, or QBism, suggests that the wave function reflects our subjective knowledge of the system, not an objective property. So the cat isn't both alive and dead, it's that we simply don't know which until we check. To grasp the core idea more intuitively, consider a dice roll inside a sealed cup. Classically, the die has landed on a number. We just don't know it until we lift the cup. But in quantum mechanics, until measured, it would exist in a mix of all 6 outcomes. Schrödinger's cat takes this further by asking, what if it's not just numbers or atoms but living beings caught in such ambiguity? This thought experiment remains one of the most powerful illustrations of quantum strangeness. It forces us to confront a world where reality isn't determined until observed, where probabilities seem to reign supreme, and where multiple versions of the universe might be unfolding simultaneously. Schrödinger's cat continues to challenge physicists and philosophers alike, not because it gives us answers, but because it spotlights the deepest questions about how nature truly works. Is the world fundamentally uncertain, or are we merely uncertain about it? Does consciousness play a role in shaping reality, and can something be real without being observed? Ultimately, Schrödinger's cat reminds us that the quantum world does not bend to our everyday expectations. It exposes the limits of classical intuition and invites us into a realm where reality is fluid, layered, and astonishingly strange. It is not a paradox to be solved, but a window into the profound mystery of existence.